Welcome to the Rocky Mountain AI Interest Group's YouTube channel. Our September meeting was entitled AI and Robotics. The following presentation was made by Harel Biggie of CU Boulder. To see other presentations that took place during this meeting and the full meetup meeting, see our YouTube channel.
Our next speaker is Harel Biggie, who's a fourth-year Ph.D. student in computer science at University of Colorado Boulder, right here, specializing in robotics. He works in the Autonomous Robotics and Perception group, advised by Professor Christoffer Heckman. He earned his bachelor's science degree in EE from University of Rochester in 2018. And his research is centered on autonomy, perception, natural language integration, and field robotics. Additionally, at CU Boulder, he served as project engineer and led the perception team for CU's entry into the DARPA Subterranean challenge. The SubT challenge was designed to accelerate the capabilities of autonomous robots in challenging underground search and rescue operations. Harel helped to lead the team to an impressive third-place ranking among renowned universities from around the world. This talk will cover Harel's contributions to the DARPA SubT challenge and explore his recent work leveraging LLMs such as ChatGPT for enhancing robot navigation through natural language commands. To illustrate these concepts in action, he'll do a live demo with the Boston Dynamics Spot platform. Please join me in welcoming Harel Biggie.
Thank you for the nice introduction. So, as Dan mentioned, I'm going to be going over foundational models and how we can use them for robot navigation, specifically on that Spot robot we saw that we'll bring into the room after this talk. So to get started here, as Dan mentioned, I was a part of the DARPA Subterranean challenge, and here you can see myself and some of our teammates as we prep a test deployment out at Edgar Mine near Idaho Springs. So that challenge was really designed to simulate search and rescue scenarios. So we had two different types of robots we sent out there, the Boston Dynamics Spot, and then the ClearPath Husky, which we can kind of see the back of it right there. And it was supervised by a team of humans, but mostly autonomous. So we can kind of see the robot going into the tunnel, and these had to go in by themselves, explore, and look for objects that would indicate human presence. So what exactly do I mean by all this, and why is this important? So as unfortunately in recent times, there's been numerous articles and tragedies where there's been earthquakes, a lot of collapsed rubble, mine collapses, people are trapped, and it's very, very hard for search and rescue teams to go in there. Putting other lives at risk to save another life is what people do on the daily basis, but that comes with inherent risk. And one of the areas that DARPA really wanted to improve is situational awareness. Can we send a robot in to get an idea of what's going on before sending another human in to make sure that it's both safe to go rescue someone and to find the people who are in the most immediate need of danger of rescuing? So how did DARPA structure all this? They created these courses ranging from urban underground environments, tunnels, caves. And there they had this group of people known as the pit crew. For us, that was 5 different people on the team and I. There was our robots that went in that we saw in the other video, modeled by Star Wars robots here. And then there was one human supervisor who will become very important. They could kind of monitor what was going on and override any kind of like high-level commands that they could see on the monitor, as you can see here, if there was communications available. That was another key component to this challenge. There's no Starlink underground. So we had to do all of that stuff ourselves, deploy our own Wi-Fi networks and everything as these robots went out. So I just want to highlight a few things at the final event. At the top, we see one of the Husky robots I mentioned. There's the full team in the next image over. As you can see, we also were competing against a bunch of universities and ended up taking 3rd place against teams like NASA's JPL, CMU, and a bunch of other world-renowned universities. So this was kind of a huge deal for CU. Thank you. So the rest of this talk, I'll kind of be going over Team Marble. That was our team name at the DARPA Challenge. A few of the perception challenges. I was one of the perception leads as well as a project engineer for overall autonomy stack. And then I'm going to go to a little bit of a shift towards language-guided navigation, which is the areas I've been more recently working in and kind of more relevant to ChatGPT and large language models. So let's get started a little bit with how do we perceive on robots. So that's one of the big things we need a robot to do. It needs to understand its environment, so then we can do actions in that environment. So for us, we had this sensor head that we developed for spots and huskies using a variety of off-the-shelf sensors. So starting with these FLIR or Gigi RGB cameras. So that gives us an idea of what's going on in 2 dimensions in color in the environment. We had these LiDARs. So there's 2 LiDARs in front here. PicoFlex flash LiDAR gives you kind of 3D depth information. The Ouster LiDAR does the same. And then we had an inertial measurement unit to kind of get an idea of the roll and pitch and yaw of the robot. So what does all that look like in reality? Assuming we have this little spot here, it's outside in a courtyard. So those are the views from 3 cameras, the left, front, and right. But what does that look like as a point cloud? So that's what some of those 3D sensors, such as the Ouster, give you up top, those little points. So you can kind of see the trees being demonstrated up there. You get this 360-degree view of the environment, and it's pretty dense representation. So that's what we kind of leverage a lot to do our navigation and planning inside the environments. So why were we sent into the environments? To find objects that would indicate human presence. These robots were sent in there to look for things like a survivor, climbing rope, backpack, anything that could indicate someone had been there and probably needed rescuing. There was also some localization for things like a cell phone that was using Bluetooth. And then there was a CO2 gas to mimic kind of a gas leak or something like that. So what does our human supervisor see? This is an example of the interface that we used that the guy standing up front of the course using a monitor was looking at. We can see that there's individual robot maps on the side. So those are generated off those point clouds that we saw, which is giving you kind of a 3-dimensional idea of what these underground environments look like. We had a merged map in the middle. So we had 4 robots out on the course at once. So that would aggregate all the maps into one view to give an overall picture of what everything looks like. And finally, all the objects that were being detected on board autonomously came up as a list, and the human supervisor could confirm what they were and what they weren't. And then they had the ability, assuming there was communication, to override anything of the autonomy stack that was not operating correctly. So let's take a quick jump into what it actually looked like when these robots were underground. So this is an example of one of the spots. You'll see the purple path. That's the spot running its onboard exploration algorithm. So it's trying to explore for new areas in the environment while avoiding any terrain that it can't go over. And while it's doing that, it's looking for all of those objects I just described. So kind of one thing to keep in mind, that video is at about 5x. So the robots were not moving that fast, but it would have been a long video otherwise. So how big were these environments? Well, they were on the scale of a kilometer or so. So here we had our 4 robots and the path they took at one of the final DARPA competitions. And you can kind of see these were like pretty much mimicked real environments, such as a subway station, tried to mimic a New York subway station. We got a little warehouse here. We have kind of a foggy area. DARPA was kind of really wanted to make it hard. They put fog because it messes with your cameras and everything like that. So we did really well at the challenge, as I mentioned, 3rd place, but there was a lot of things to be improved. At the challenge, the top scoring team only rescued about 50% of the artifacts, which means a lot of room for improvement. You don't want those odds if you're the ones out there needing rescuing. So one of the ways we think we can improve that is jumping into using large language models. That human supervisor interface I mentioned is great if you are getting a PhD in robotics like I am. But if you're not, using one of these robots would be really difficult with that interface. So that's why we think that doing something like natural language is far more appropriate for this. So for example, we could tell the robot to go down the hallway until you find the backpack and then turn left. And that command will let it just execute there and do that rather than clicking like a little waypoint here, move the waypoint as it progresses, which is a really slow process. And when time is of the essence, you really want something more efficient. So we were able to do this leveraging code generation abilities of ChatGPT. So you can see here the robot is looking for something to do a kickflip on. In other words, realize it needs to do a skateboard. You can do something a little bit more helpful, such as if firefighters were using the robot, they could look for a fire hydrant. We can tell it to go to specific people, like distinguish the person's on the table as opposed to a person who's not. We can specify the color of an object, look for the white fan, and have the robot navigate to there. And this is all being done using ChatGPT as the backend to generate code based on the natural language prompt. So what is one of the key challenges that faces robotics and doing this type of navigation? It's called language grounding. So we have the sentence here, go to the blue bin on the left of the red backpack. And everything in that sentence needs to be associated to either the physical environment or an action on the robot. So for example, we need to associate the word blue bin with that blue bin in the actual image. And red backpack needs to be associated with the red backpack. Now that looks pretty simple if we as humans are doing it, or maybe you could run an object detector and do that. But the big challenge comes with the ambiguity in language. So taking an example like this, go to the chair on your left. One could think it's leftmost chair, or it could be this chair, but that really depends on what your intent and specification was, which is one of the areas we're actively trying to resolve to make sure robots go where we want them to go. So with that in mind, I'll dive a little bit more into a contextual example here. So we have the sentence, go to somewhere where I can watch a movie, and this is the scene. So we want the robot to end up going to a chair or something like that where it can see the movie. So as I mentioned, this is being done using code generation. So this is code right here is all being generated by ChatGPT. So it's looking for a TV or a screen, and then it's finding all of those. And if it finds nothing, it will, of course, return an error. And then it's looking for anything that relates to a couch, chair, or anything like that. And then we are trying to find the closest one to the TV. And that's where we end up sending the robot to. So we have a little video here going. So it ended up going to that chair. We can't see it in the frame, unfortunately. The videography was not the best when we were running this experiment, but the TV is kind of where those cones are in the background. So I'd like to thank all of the collaborators in the DARPA challenge, and especially my lab, the Autonomous Robotics and Perception group, as well as my advisor, Christoffer Heckman. And now I think the fun part is going to happen. We're going to actually be showing the spot and doing some of the live demos. And while we're setting that up, I'll show a few more commands from our system. So this is an example of multi-agent navigation where we are using language to control both spots. So Dusty, if you want to walk the spot around the room just a little bit so people can get a good view of it. Dusty wasn't introduced, but Dusty is the lab manager in our group. Very nice of him to help out for this. So Dusty, if you want to, yep, perfect. So now I'm going to, on my interface over here, I'm going to tell the robot to go to the fire extinguisher. And this will just take a little bit. It takes about 30 seconds to a minute. That's one of the limitations of these methods. It's a combination of how long it takes to query ChatGPT, go over the internet. Then we have to send our images back to a server to process. So this is actually running on a 4090 back in our lab. So part of it is also we're using a cell phone hotspot. So it just takes it a little bit of time. CU's wireless doesn't play well with our robots for some reason. So Dusty, if you want to send the robot. And unfortunately, I can't really show this. I can kind of show the screen to people here, but this is kind of what we see on our end with the generated code in the image. So that's kind of what the robot can do. We could try to send it to a few other things, maybe the black cart next to Dusty. So, sorry, it's a little hard to type one-handed. So I just sent over the command. Go to the black cart. So we're having the robot identify that black cart right now. So right now it's generating a piece of code that's going to have something like find a cart, verify the cart is black. And then we're going to do a 3D projection. So taking what it found in our 2D cameras, we associate that with that 3D point cloud that we saw earlier on the Ouster LiDAR. And then we get a 3D waypoint that we can have the robot follow to. So we do that using what's known as a path planner. So that's kind of running a grid-like search inside the maps that I showed earlier. So unfortunately, Dusty, the black cart in the lighting here did not show up so great. Yeah. That's one of the challenges we do face a lot with specifically these camera models. The auto exposure in some of these lighting conditions is not as great. Yeah, that's why we have, I mentioned the 5-watt LEDs. If people in the front want to look away from the robot, Dusty, if you want to just turn them on real quick. Other side? No. Interesting. So there are, on the sides here, we do have like really bright LEDs that we try to create our own lighting conditions underground to help with a lot of these issues. These cameras work really well under constant lighting conditions. So, and as the previous speaker mentioned, like hardware is really hard. One of the reasons we went with these cameras is we found that USB cameras were just very, very unreliable, especially underground. So the robot would have a lot of shock and vibration, and those USB connectors are quite flimsy. So Ethernet and machine vision grade cameras are far more reliable in that sense. Yeah, so you can send it over to that cone. Yeah, and it should figure it out. Yes. Yeah. Try to send it again. So as you can see, this is all like research, a little bit work in progress, but no, because we can actually see which one it found here. But it sometimes there's a whole mapping piece that goes along with here that it's generating online. There it goes. Maybe. No, I think it's gonna come back around. Yeah. So like I said, this is early kind of work into associating large language models with robot navigation. So we have plans to improve this obviously going forward, but that's kind of what I have. And if you guys want to maybe see the robot, we can walk it through the aisles real quick, if there's time for that. So just make sure your feet are kind of away from it. It shouldn't hit you, but I'd say probably around 60 to 70 pounds or so with all of the stuff on it. Yeah. Yeah, it can carry up to 14 kilograms on top, which we have about 11 on there right now. Any other questions about the robot? That's a good, with an academic discount, the base. Question was, what does it cost? With the academic discount, it's about 80,000 for the base alone. And everything from the black part up is, which we put on, is probably another 20,000 or so. So $100,000 or so is around the price tag for all of this.
Hey, please join me in thanking the speakers for just an awesome presentation.